Okay, so I'll start by motivating the need for primordial magnetic fields. And we detect magnetic fields at different scales in the universe, starting all the way from planets, solar systems, galaxies, clusters of galaxies. But more importantly, we also detect magnetic fields in the voids between the clusters of galaxies. And the origin of magnetic fields at all these different scales, especially on the large scales, is unknown. And in particular, also the origin of micro-Gauss scale magnetic fields in galaxies are unknown. So these are correlated on kiloparsec scales or several kiloparsec scales. And we don't know where these magnetic fields came from. And we have three different kinds of scenarios. So these magnetic fields can either have originated during inflation, during early universe phase transitions, or by the amplification of very small, tiny seed magnetic fields by galactic dynamos. Dynamos are essentially processes that are fluid motions are converting, amplifying magnetic fields, taking small magnetic fields and amplifying them to larger scales. Now, the scenarios 1 and 2, inflation and phase transitions, they are called primordial magnetic fields because they are generated very early in the universe. And to explain the micro-Gauss scale galactic magnetic fields, what we need is nano-Gauss or less than a nano-Gauss scale, about from 0.1 or more nano-Gauss scale magnetic fields which are correlated on megaparsec scales. So you can take those around 0.1 or higher nano-Gauss magnetic fields, which are correlated on megaparsec scales. They can get adiabatically compressed during the start of structure formation to give rise to the micro-Gauss scale magnetic fields in galaxies. So this is what we call the primordial scenario, that without any help from dynamos, you can explain the micro-Gauss scale magnetic fields in galaxies. On the contrary, if you have magnetic fields weaker than 0.1 nanogauss, they can't get amplified to micro-Gauss scale just from compression, and you need some dynamo effects to amplify them to the presently observed magnetic fields. Now, the reason primordial magnetic fields are an attractive scenario is that they can explain the uniform distribution of magnetic fields in the voids. So one could think that the magnetic fields in voids could have come from, they were generated in the galaxies or clusters of galaxies, and then they were pushed out by some MHD processes and filled the voids. But we have sort of a very uniform filling factor in the void. So it's not that the magnetic fields are very strong close to the galaxies and they get weaker. They don't get substantially weaker. So we prefer the primordial scenario that the magnetic fields were already present in the voids prior to structure formation.
And just a question, what's the evidence for that? So there are measurements of that?
Yeah, so this is the non-observation of photons from TV blazars.
Okay.
So we are looking at TV blazars from far away, and they are passing through the intergalactic matter, and they cascade and into electrons and positrons, and they would later combine to give you GeV photons. So you can expect how many GeV photons you can see if there are no magnetic fields. But if there are magnetic fields, the electrons and positrons will go in different ways, will not combine, and you'll get much lesser GeV photons than you expect if there are no magnetic fields. And based on that, you can put a lower limit on magnetic fields in the voids. Sure. So there's been recently some work on trying to use primordial magnetic fields to solve the Hubble tension. So I think everyone here knows what the Hubble tension is. It's a 5 sigma discrepancy between local and high redshift measurements of the Hubble constant. Supernova measurements are giving us a high value of 73.04 plus minus 1.04 kilometers per second per megaparsec, while measurements of the CMB are giving us a lower value of 67.4 plus minus 0.5. So it was seen when Gedantic and Savelya were doing some MHD simulations, they were seeing that if primordial magnetic fields are present in the primordial plasma prior to recombination, these were leading to baryon clumping on kiloparsec scales. So the result of that baryon clumping was that recombination was happening a little bit earlier, and this reduces the sound horizon and increases the Hubble constant to be consistent with the supernova measurements. And it was seen that a 0.1 nanogauss level primordial magnetic field before recombination was enough to resolve the Hubble tension. So primordial magnetic fields, as I mentioned, could be generated during inflation or during phase transition. So let's talk briefly about the basics of inflationary magnetogenesis. Primordial magnetic fields can arise from vacuum fluctuations during inflation. And what happens during inflation is these quantum fluctuations are generated, they're pushed outside of the Hubble horizon during the exponential expansion, and they have very large correlation lengths. And similar to the matter power spectrum, they scale invariant on very large scales. The other thing is magnetic fields. So the action describing the magnetic fields is F mu, the Maxwell action, and this is conformally invariant. So it just magnetic fields produced will just dilute with the expansion of the universe as 1 over a squared, a being the scale factor. So the magnetogenesis mechanism should involve some form of symmetry breaking, which breaks this conformal symmetry. So you can either couple the tensor with curvature or a function of a scalar field. Now this may or may not be the inflaton, but it's some scalar field in operation during inflation. So what this makes is that it doesn't let the magnetic field dilute as fast with the expansion of the universe as would happen if you don't break the conformal symmetry. So you get a substantial magnetic field at the end of inflation. They result in scale invariant or nearly scale invariant power spectrum, which is not the case for phase transition magnetic fields. Now, for phase transition magnetic fields, what you need is you need a first order out of equilibrium phase transition. And the way it's generated is you have the old phase and bubbles of the new phase are nucleating inside the old phase. And as these bubbles expand, the magnetic fields are generated at the surface of these bubbles. They grow, they expand, collide with each other, and fill the space with the new phase, and you have magnetic fields. These all involve violent bubble nucleation, and they generate significant turbulence. The problem is, we know that there are 2 phase transitions in the early universe. From cosmology, we know about the electroweak phase transition, the QCD phase transition. And in the standard model, none of these are first order transitions. So to explain magnetic field generation from phase transitions, we need some beyond the standard model extensions to make them first order. These can involve supersymmetry or some more exotic physics. And in a way, this makes us, there's no evidence for any of these models so far. None of these models that extensions that make the phase transition first order. So it's a little bit more natural to prefer inflationary phase transition because they don't involve any exotic new physics, but the jury is still open on whether it's inflation or phase transitions.
And is the idea that they're not being first order that you don't get bubbles? Like, could you say a little bit more about what happens?
Yeah, you don't get bubbles, so the magnetic fields are not very strong enough. So if you don't have turbulence, you can't even amplify the magnetic fields significantly on large scales. Yeah. So let's talk about the problem that I'm going to focus on. It's the magnetic field in galaxies. So the idea is if we want to explain the magnetic fields on galaxies, micro-Gauss level magnetic fields on galaxies, just from inflation, we need to have scale invariant magnetic fields above 0.1 nanogauss, which are correlated on megaparsec scales. And they were, during structure formation, they were adiabatically compressed to micro-Gauss scale fields. And the reason that I'm focusing on the 0.1 nanogauss number is because of magnetic flux conservation. So let's say we have a cloud of baryonic matter prior to structure formation, which is hosting a 0.1 nanogauss level magnetic field. If that megaparsec scale cloud collapses to around a 10 kiloparsec scale structure, just from flux conservation, we get a micro-Gauss level magnetic field. And the reason I'm focusing on this number 10 kiloparsec is because that's a conservative kind of lower limit for baryonic matter in galaxies, in a typical galaxy. So if I'm able to detect scale invariant magnetic fields above 0.1 nanogauss, that will be an evidence for inflationary primordial magnetic fields, because phase transition magnetic fields cannot generate fields with strengths higher than 0.1 nanogauss. So if I'm getting a scale invariant magnetic field which is that high, which is more than 0.1 nanogauss, it will be an evidence of inflationary primordial magnetic fields. And more importantly, it's a compelling evidence of inflation itself. However, if I'm constraining my scale invariant magnetic fields to be below 0.1 nanogauss, then I know that just from the flux conservation, just from adiabatic compression, I cannot explain the microgauss scale magnetic fields. So inflation isn't the primary source. It needs to have some help from dynamos, because inflation is giving you some magnetic fields and that has to be amplified by dynamos. So how do you constrain the strength of primordial magnetic fields by a CMB? So primordial magnetic fields induce temperature and polarization anisotropies in the CMB. And people have calculated a lot about how these perturbations look like for different kinds of magnetic fields. The problem with all these is that the CMB spectra scale is the fourth power of the magnetic fields. So if you reduce the sensitivity from future experiments, if you reduce the sensitivity to, if you reduce the error bar of the CMB spectra by a certain amount, it doesn't give you that much advantage because it scales as b to the fourth. On the contrary, we can look at something called anisotropic birefringence or Faraday rotation. So Faraday rotation is, if I'm looking at the plane of polarization of the CMB, because it passes through magnetic fields present, primordial magnetic fields present, its plane of polarization will be rotated. That is called Faraday rotation or birefringence. And we are looking at anisotropic birefringence because the magnetic field strength is slightly different. It's a Gaussian random field. So its strength is slightly different in different directions. So I'm looking at the anisotropic birefringence, and that can be a good way to constrain primordial magnetic fields because the amplitude of the anisotropic birefringence scales is b squared. So if I'm able to improve the sensitivity on anisotropic birefringence measurements, I can really nail down and constrain primordial magnetic fields very strongly.
And just a question, you said yourself with the combination, but with birefringence, you'd also be sensitive to it happening anywhere, right?
Yeah. So the biggest problem is magnetic fields in the Milky Way, but I'll come to that later.
Okay.
Yeah, there's a contamination there.
Yeah. Okay.
So
question.
Sure.
Maybe I misunderstood something earlier when you were talking about the inflationary genesis of the magnetic field.
Mm-hmm.
It seems to me you put in the Maxwell action by hand, the F mu nu term.
Yeah.
So in what sense is inflation actually generating this field, or is it just inflating it?
Okay, so the sense in which inflation is generating it is, if you have couplings like that, let's say coupling with the curvature or with some function of the scalar field, if you look at the evolution equation of the magnetic fields, they don't dilute as 1 over a squared as the universe expands, but they dilute with 1 over a to the some very small power, which means they don't scale down, so they don't dilute as fast as you would expect without those couplings. So at the end of inflation, you'll have a significant amount of magnetic fields left.
Okay, but the inflation you're putting in ab initio, right? I mean the magnetic field rather.
Right. Yeah. So it's some hypermagnetic field because it's prior to the electroweak phase transition. But yes, so you're putting those terms. You can just take them to be generated during the quantum fluctuations. But the idea behind those couplings is that you don't let them decay as fast as 1 over a squared. They decay much slower than 1 over a squared.
Okay, thank you.
Sure. So birefringence is therefore a way to provide a very tight bound on the primordial magnetic field strengths from future surveys. Now, the thing that we do in our work is take a realistic primordial magnetic field spectrum. Now, primordial magnetic fields are, as I mentioned, the Gaussian random field. So in Fourier space, they're characterized by a power spectrum. And the power spectrum has a single power loss slope. Traditionally, that's the thing people take into calculations. So for an inflationary magnetic field, or scale invariant magnetic fields, the energy spectrum, which is k squared times the power spectrum, has a k to the -1 slope of very large scales. But it is very well known from MHD simulations that there's an effect of turbulence, which on relatively intermediate scales for the inertial range, it modifies the spectrum a little bit. It modifies it from k to the -1 to give a k to the -5/3 spectrum. And so when people are calculating the effect on matter path spectrum or CMB, they don't typically take these calculations because it's slightly difficult to handle analytically or to do it in simulation. So people just go with the traditional spectrum, which is the black line. But if you include the turbulence, it modifies the spectrum, and the effect that it most importantly has is it redistributes the power on large scale. So it increases the power a little bit on large scale, and that will give a stronger birefringence signal. The good thing about looking at birefringence from scale invariant magnetic fields is that the birefringence signal is on large scale, it's very much independent of the multipole you're looking at. So you can look at very small multipoles and put a constraint on megaparsec scale magnetic fields. So we use this spectrum to theoretically calculate the anisotropic birefringence signal given a scale invariant magnetic fields. And now, once you get the theoretical calculation, so I can just give a brief overview of what's going on. You're looking at the rotation angle. So this alpha n is not just the angle, it's the angle by which the plane of polarization has been rotated in a given direction. Take a two-point correlation function and get a CL alpha alpha path spectrum. And the amplitude of the path spectrum is given by L plus 1 CL alpha alpha by 2 pi, which is independent of L because of scale invariant magnetic fields. And the very critical thing here is that because it's a birefringence caused by magnetic fields, it has a frequency dependence. So this amplitude depends on inversely on the fourth power of frequency. And this can be used to distinguish it from birefringence caused by other things like axion photon couplings, Lorentz violating physics, primordial gravitational waves. It can all lead to birefringence signal, but this frequency dependence will tell us what's the essentially let us distinguish the magnetic field caused birefringence. And we know the error bars on A alpha for future CMB experiments like SO, S4, and CMB-HT. And these are known numbers. So we see that even compared to ACT pole or SPT, the constraints on birefringence from CMB-S4 and CMB-HT are very, very tight. So we can use that to constrain primordial magnetic fields very tightly. And when we compare our theoretical calculations, we get the corresponding constraints on the strength of scale invariant magnetic fields. So SO will be able to put an error bar of 0.47 nanogauss. CMB-S4 will tighten it further to 0.08. And CMB-HT is capable of giving a very tight constraint of 0.036 nanogauss. So this is much lower than the 0.1 nanogauss level that we are used to distinguish between the inflationary and dynamo scenarios. Now, we know that current best constraints in sigma BSI come from Planck and SPT analysis of the CMB spectra. And this is at 1.2 nanogauss. So future CMB experiments looking at birefringence will be able to nail it down to much, much lower levels. And this is because CMB-HT is improving the bounds on A alpha by 4 orders of magnitude. So CMB-HT has the capability of giving the tightest constraints on primordial magnetic fields, scale invariant magnetic fields.
Are you using the scale dependence? Means I'm guessing that like the 30 and 40 gigahertz data is useful there, or is it contaminated by 4 grams? Like,
it's contaminated. So we're mostly using the 90 and 150.
okay, so just basically that.
Yeah.
Different.
Yeah.
Okay.
So this is, in a nutshell, what's the conclusion of this work? That if you detect scale invariant magnetic fields in the red region, then you know that it is from inflation because the division is 0.1 nanogauss. So anything stronger than 0.1 nanogauss, it will tell you that it has to be from inflation because nothing can generate such a strong magnetic field, scale invariant magnetic field on megaparsec scales. So if you detect something in this red region, you know it's an inflationary magnetic field, and consequently it's a very strong indication for inflation. If you detect something in the green region, if you detect your strength of scale invariant magnetic fields on megaparsec scales below 0.1 nanogauss, then you know that the origin of magnetic fields must be from galactic dynamos. So the initial seed could have been generated from inflation or phase transition. So if it's a scale invariant magnetic field, it has to be from inflation, but the inflationary magnetic field itself, by itself, is not enough to give you a microgaussian magnetic field. You need to have amplification with dynamo. On the contrary, if you have something in the red region, you know its inflation is sufficient. It can have help from dynamos, it can give you a much stronger field, but it doesn't need to. And if you are able to put an upper bound, so this is the 95% confidence level upper bound that CMB will be able to put. So if you're putting an upper bound in this green region, then you can rule out inflationary magnetic fields. And the CMBS for confidence, like 2 sigma upper bound is there. So this is important because CMB has the capability to rule out inflationary magnetic fields. And most importantly, if you look at the number, CMB sigma BSI is 0.436 nanodals. This also implies that if CMB is to detect an inflationary magnetic field, that is a scale invariant field over 0.1 nanodals, it can do that at least 3 sigma significance, which is also very interesting result. But as you were mentioning, like we can have contamination. Now, the primordial magnetic field is strongest right after recombination because it dilutes with the expansion of the universe. So we don't need to bother about primordial magnetic fields after that. But you can have primordial magnetic field. You can have magnetic fields in the Milky Way. Milky Way has a similar like 0.1-ish nanogauss magnetic field all over the place from other sources. So how do you know that the signal that we see is from primordial magnetic fields and not from the Milky Way? So the good thing here is that people have mapped out the birefringence or the rotation of the plane of polarization in the Milky Way. They have looked at 40,000 extragalactic sources and calculated the rotation measure spectrum. So I was telling you that the birefringence signal is proportional to the 4th power of frequency, inversely proportional to the 4th power of frequency. If you take away the frequency dependence, you get another quantity called rotation measure, which is just the frequency independent part. It's just multiplied out with nu to the 4th. So people have mapped out very precisely, looked at 40,000 polarized extragalactic sources. This is called the NBSS catalog, so NRAO, very large survey, sky survey catalog. And they have mapped out the rotation measure spectrum and the corresponding error bars for the Milky Way. So we know how the Milky Way looks like. So we just need to take that spectrum and see whether the error bars on Milky Way magnetic fields that we can see through our birefringence constraints interferes with that, or is it much lower, or whether it throws a wrench into our calculations. So they are looking at the NBSS catalog. They know what the rotation measure is. And the reason we can do that, it's the most crucial thing, is that the magnetic field induced Faraday rotation or birefringence is frequency dependent. So they can measure at multiple frequencies what the rotation angle is and actually nail down the contribution of the magnetic, the Milky Way magnetic field. So they're taking different masks and calculating the Milky Way rotation measure spectrum. So since experiments like CMBS4 and CMBHT are going to measure a sky fraction of 0.5, it'll be closest to our results if we take the spectrum for X sky of 0.4. So we take the cleanest 40% of the sky, look at what the Milky Way rotation measure spectrum is, what the corresponding error bars are, and calculate what's the error bars to the scale invariant magnetic fields there. And what we find is that the error bars on the scale invariant magnetic fields coming from the galactic contribution is 0.006 nanodals. And remember that the CMB error bar was 0.436 nanodals. So we have an order of magnitude difference, and we can, with confidence, subtract the Milky Way birefringence from our measurement. So we know that our calculations stand. So just to reiterate this part of the discussion, the current 95% confidence level upper bound is 1.2 nanogauss from CMB Spectra, which is the TTTEE of Planck, and SPT gives the BV polarization measurement data. We can constrain it at 1.2 nanogauss. And looking at birefringence measurements from CMBS4 and CMBHD, that error bar will be nailed down to 0.08 and 0.036 nanogauss respectively. And the CMBHD error bar is below the 0.1 nanogauss threshold that distinguishes between the purely inflationary dynamo origins of galactic magnetic fields. If we detect a magnetic field scale invading fields below 0.1 nanogauss, it will indicate a dynamo origin. On the contrary, if we detect above 0.1 nanogauss, it will be a compelling evidence for inflation. And CMBHD is capable of detecting inflationary primordial magnetic fields at 3 sigma or higher significance. So I was talking about ways to detect inflationary magnetic fields. And we are not, the reason birefringence is not good enough to detect or constrain phase transition magnetic field is because the phase transition magnetic field spectrum is causal. So instead of having a k to the -1 dependence, it is a k to the 4 dependence at large scales, at low k. So the birefringence signal is extremely weak, and it's very hard to, we can't conceive of experiments, at least in the near future, that will be able to constrain that. So we can look at something else. We can look at primordial gravitational waves. And the reason primordial gravitational waves are interesting is because it doesn't care about whether the universe was opaque or transparent to electromagnetic radiation prior to recombination. So if you have a process in the very early universe that generates gravitational wave, the gravitational waves just dilute with the expansion of the universe. They don't couple with anything electromagnetic that's going on. So the universe is opaque to electromagnetic radiation before recombination. And gravitational waves can therefore be a good instrument to peer into these early times. So if you can predict detectable gravitational waves from any early universe process, it can give a good indication of the physics that was going on during those early times. And gravitational waves can be generated at the epoch of phase transitions. And we calculated through numerical simulations of magnetohydrodynamic processes. So these are potentially detectable from Lee summation. So just a quick recap of the phase transitions. The bubbles of the new phase are nucleating randomly. These are very violent processes because the bubbles are nucleating, they're colliding with each other. There are different kinds of collisions, but depending on the initial conditions, like how fast the bubbles expand and how many of them collide within a given amount of time. But whatever the thing is, they're generating a significant amount of turbulence. So not only is the magnetic field giving a lot of energy and disturbing the space-time metric, all this turbulence is also giving a lot of random stochastic energy into the field, into the space-time, and generating gravitational waves. Again, these two phase transitions are important, and we are looking at the electroweak phase transition because the QCD phase transition, I think, it's more or less accepted that this is not a first-order transition, and there are not too much efforts in going into trying to make it a first-order transition. So we'll focus on the electroweak phase transition. So, as I said, the interaction between the primordial magnetic fields and the fluids leads to magnetohydrodynamic turbulence, and the turbulence is characterized by the energy spectrum of the fluid and the magnetic fields. So the fluid velocities and magnetic fields both are extremely turbulent, and they have their respective energy spectrum that they talk to each other and influence each other through MHD. And we are going to see how both of these influence the gravitational wave spectrum in the early universe. So gravitational wave energy and the characteristic amplitude, which are the two detectable things by LISA, they depend on the type of turbulence. And we'll numerically model these observable gravitational wave signals. So just a quick recap, Gravitational waves Hij are the tensor perturbations above the basic Friedman, Robertson, Walker background of the universe. And in the radiation dominated epoch, so all of these phase transitions happening deep inside the radiation dominated epoch, we can make an approximation, and the gravitational wave equation looks like this, where Tij is the source. And this source is the source that generates the gravitational waves, and this is sourced by both fluid velocities, which are marked in blue, and the magnetic field contributions. And these UIs, the fluid velocities, and the BIs, the magnetic fields, they talk to each other through a set of very complicated MHD equations, which we are numerically solving. And Lisa provides sensitivity curves for two quantities. One is the gravitational wave energy density as a function of frequency at the present time, and the characteristic amplitude of the gravitational waves at the present time. The energy density is written as omega because it's typically normalized to the critical energy density at the time of the generation of the gravitational waves. And the crucial point is that the detectability of gravitational waves depends on the initial conditions for the MHD turbulence. So what kind of turbulence the early universe starts with impacts whether we can observe the gravitational waves. So we consider three kinds of initial conditions in our simulations. One is where we take the initial magnetic field to be just randomly switched on and fully helical. Now, helical magnetic fields means that there is a left-right asymmetry in the configuration of the magnetic fields. One way of physically thinking is that the magnetic flux tubes are interlinked with each other. That's giving you helicity. Helicity is essentially, mathematically thinking, it's the quantity A dot B, where A is the magnetic vector potential. It's A dot B averaged over the entire space. So if you have a non-zero helicity, it implies that the generation mechanisms generate the gravity that generates the magnetic fields involve some kind of parity symmetry breaking. So the reason helicity is important in turbulence is because if you have a helical magnetic field, it leads to something called inverse cascading turbulence. And it gives a lot of energy as magnetic MHD decay, MHD evolution occurs. It pushes the magnetic fields to have a lot of energy on larger and larger scales, instead of the energy going to smaller and smaller scales. So we consider the first initial condition to be whether suddenly the magnetic field is switched on, it's fully helical, and there is no forcing. We consider a second case where we have hydrodynamic turbulence, and there is initially zero magnetic field, but at a particular scale, we start giving an electromagnetic force into the plasma and see how the gravitational waves are generated. And in the third case, we have an initial, we again have the same starting condition, no magnetic fields to start with, but we give a fluid, there's acoustic turbulence because we suddenly force the fluid to have a certain kind of forcing. The important thing that we see in all of our simulations, and which was previously not seen by analytic and semi-analytic arguments, is if you are starting with a certain configuration of magnetic fields, at phase transition, you have that k to the 4 dependence, just from causality, you have the k to the 4 dependence on large scales. It was always expected that whatever your magnetic field or fluid velocity spectrum is, the gravitational wave spectrum is shallower by k squared. So the expectation was that on large scales, on smaller scales, you have a k to the -5 by 3 for magnetic fields. You have a k to the -11 by 3 for gravitational waves, which is just shallower by factor of 2. This just comes from the gravitational wave equation and number counting. So it was also naively expected that if you have a k to the 4 on large scales, you have a k squared for gravitational waves in small scales, but the numerical simulation showed that that is not the case. So the analytic expectations were not right. You have a more or less flat spectrum on larger scales. What it means is that you have more energy on larger scales. So this will correspond to the frequency range of interest for Lisa, and you have more gravitational wave energy than previously expected. So you bump up your chances of detectability. So In the inertial range, this is the expected thing. But in the subinertial range, which is this large scales, we discovered a flat gravitational wave spectrum, which is a new feature never seen before in analytic calculations. So we calculate for all these different kinds of initial conditions. We calculate the gravitational wave spectrum and compare them with the LISA sensitivity curves, which assume a mission duration of 4 years. And what we see is that for runs with an initially helical magnetic field, we need an energy input about 3% of the total radiation energy density. If that goes into magnetic fields and the fluids, you can generate gravitational waves of sufficient strength to cross the LISA detectability threshold. On the other hand, if you're going to the second initial condition, which is you have an electromotive forcing, solenoidal electromotive forcing, you can have 4% of the radiation energy density going into the magnetic fields. You can cross the LISA detectability threshold. The surprising thing was that if you're doing an acoustic turbulent forcing, that requirement is much lower. It's just 0.5% of the total radiation energy density can go into the magnetic and fluid velocities to cross the LISA detectability, which means acoustic turbulence is much more efficient in producing gravitational waves than solenoidal turbulence. And yeah, so this is roughly this is what the plots are. So for the first case where you have an initially helical magnetic field, you see that around 0.01 Hertz, and in this range it crosses the LISA detectability threshold, both for the energy density and for the characteristic amplitude. And I was just mentioning the flat gravitational wave energy spectrum, which in frequency space, it just corresponds to a proportional to F frequency shape, which was also not seen. People thought that this was going to be much shallow. And this is actually what this is widely thought that the omega GW, the normalized energy density as a function of frequency of the gravitational waves, would be proportional to the third power of frequency, the subinertial range. But from the numerical simulations, we see that it's not that, it's much shallower, and this enhances the detectability. So the first set of runs assumes that you suddenly have a magnetic field all over the place, which is a little unrealistic because magnetic fields you're suddenly switching on magnetic field, but that's not how magnetic fields are generated during phase transitions actually, because you have those bubbles colliding. There's a typical length scale associated with the bubbles. So you have a turbulence associated, like there's an injection of energy at a particular scale. So that's why we do the second and third set of simulation. But we don't really know whether the forcing is solenoidal or acoustic. So we do both of these simulations and we see that the acoustic forcing is much more efficient in generating gravitational waves than the solenoidal forcing. But in all of these initial conditions, this shallow proportional to F low frequency behavior is seen to be of a universal nature. This is independent of the initial conditions. This is seen across all of the set of simulations. And this is what actually enhances the detectability. So the high frequency slope is steeper than before. So this was from previous calculations, it wasn't seen that this slope falls off at high frequency that fast. So this is also something we discovered, but that's slightly less important than the shallow low frequency behavior. And when you are forcing the magnetic fields instead of the first set of simulations, you also produce a bump at a certain frequency where you're injecting the energy. This actually leads to a higher gravitational energy and increases the detectability. So yeah, so that is my conclusions. Thank you.
Thank you so much for a very nice talk. Are there any questions?
I have a question.
Sure.
Just going back to the earlier part about detecting the on this topic of birefringence,
Mhm.
you talked about the importance of showing that it was scale and variance.
Yes.
And so I wanted to know, do you actually get to constrain the scale dependence with the data? Like, how does that feed into it?
So when I'm theoretically calculating A alpha,
Yeah,
it doesn't matter. Like I can go up to L sub 30 or 40. It doesn't matter. It's the prediction is essentially the same.
yeah,
So if you go to high, so let's look at the plot for. So if I'm going to L's corresponding to this range,
yeah,
that's when the scale dependence will start. But
yeah.
that will correspond to very high L measurements. So we haven't really looked at that because this will anyway give us weaker constraints than on smaller L's. So this is going because the signal is highest here, and that's what we are interested in.
But what if you, for example, tipped that whole spectrum and made it like a different shape? Would you be able to tell that that's not, because you're only getting one number out at the end, A, right?
Right.
So can.
So if I change the spectrum,
Yeah.
that's going to give me an L dependence.
Yeah.
Because then the signal will be different at different times.
Okay, so can you see that?
Yes, yeah. So what will happen is that the other way of thinking about this is if I have phase transitions, the only other allowed shape is A to the 4. So your spectrum will go like this. So you have very low signals at large L's.
Yeah.
And you'll get, like when you already have a lot of noise, you'll get a slightly higher signal. But the other thing to keep in mind is that this whole amplitude will then be lower because inflationary magnetic fields are much stronger. Phase transition generated magnetic fields are weaker. So the total signal will also be low. Even though the L dependence will change, the total signal will also be low. So it will be beyond the threshold of modern instruments anyway. So it's hard to do that because it's not just the shape, it's the overall normalization that also matters. Sure.
I have a question. Can you hear us?
Sure. Yeah.
Okay, thanks. Because so regarding the inflationary magnetogenesis, I remember a paper by Takeshi Kobayashi and Daniel Green that they had like some very generic like kind of theorems that said that was always difficult to generate magnetic fields during inflation without also generating very, very strong electric fields, and then this screwed up the whole magnetogenesis in some way, which I don't know. Now I don't remember. Are you familiar with this paper? And if so, can you comment about that? Or
I'm not very familiar with that paper, but
yeah,
yeah, even if you generate electric fields, because after recombination, the plasma is like highly conductive, right? So you short out the electric fields very soon anyway. So yeah, so there are many models of magnetogenesis, like inflationary magnetogenesis, that suffer from like two main problems. One is called the back reaction problem. That is, you generate magnetic field sufficiently strong that it screws up your evolutions. It inputs a lot of energy that disturbs the vacuum state of the universe. So that is called the back reaction problem. It back reacts and changes the entire evolution, like the A of T dependence. The other thing is called the strong coupling, and which means that you're doing a perturbative analysis to calculate the magnetic field strength, and your equations are not self-consistent anymore because the effective charge becomes much, much higher. So I'm sure there are multiple models that can evade these problems are tough to evade, but there are multiple problems that can evade these problems. But I'll be very interested to look at the paper anyway.
Okay. Yeah,
sure.
sorry that I cannot also remember very well the content, but I will send it to you later. Yes.
Yeah, sure. Yeah, that'll be lovely because what all these models assume is that even if electric fields are generated, they're shorted out, so they don't get much time to affect the evolution anyway.
Thank you.
Yeah.
Are there any other questions?
I was wondering about also this first part. When you said that CMB4 and CMB HD will do much better, which is I assume because they will have higher resolution and less noise on.
Yeah.
IL. What are the sort of instrumental systematics that you're worried about? When I think about polarization angles, I always get worried, and I'm not sure if these upcoming experiments will do much better than we currently do. But perhaps you're sensitive to overall polarization angle systematics.
Yes,
Is that the
because
case?
because these are calculated just from how much. So these error bars are calculated based on how much E modes are rotated into P modes, and I think the noise spectrum is insensitive to the overall angle. So I don't think. I think these are pretty robust.
Okay, so
But yeah, I'll need to be very sure. But I think that's what my thought is.
okay, I guess, okay, so because it's an L dependent, so an overall calibration error is sort of a monopole in this measurement.
Yes,
It
and
doesn't
this
matter.
will go away, yeah.
How you think about it? Okay,
Because these calculations also go from like 500 to when they're reconstructing the noise.
Yeah.
From 500 to 2000. So we don't deal with the monopole anyway. So
Yeah.
Okay. Yeah.
okay,
Sure.
I think we had a similar thing for ACT with Toshiya's paper.
Yeah,
on,
yeah.
Right, Birefringence, that then you're exactly, your monopole, you're not sure of, but then the parallel.
it doesn't really,
Doesn't matter.
okay, yeah.
I mean, these are Toshiya's limits anyway.
Ah, okay. Fine, sorry. Very good.